All right, we will go ahead and get started. Welcome, everyone. My name is Ashley Corzin, and I'm from NASA Langley Research Center. I'm the U.S. Chair of the International Organizing Committee for the International Planetary Probe Workshop, or IPPW. This is our first in a series of webinars, excuse me, sponsored by IPPW, taking place over the next several months. So thank you again for those of you that are new to this workshop and are going to hang in there with this exciting format we're trying out this year. For those that are not familiar with IPPW, this would have been our 17th event this year. Unfortunately, we're not able to hold the event in person, so that's why you're hearing about the webinar series here today. IPPW involves engineers and scientists interested in the in-situ exploration of the planet and the important technologies that support entry, descent, and landing that make these missions and these scientific investigations possible. Traditionally, our workshop is an in-person event held 1 week every year and has alternated between Europe and the US since its inception. We think back around 2003 is probably the first workshop. Our meeting this year was supposed to have been held in Monterey, California, but unfortunately we did have to cancel the in-person event due to the impacts associated with COVID-19. The webinar series that's beginning today is intended to maintain levels of engagement through the international community working and interested in these disciplines so that we can kind of continue to have that scientific and technical interaction that we would have had in person this summer, but do it in a little bit different format this year. We also want to use this webinar series to lay the foundations for what will be our first meeting in the Asia Pacific region, as Tokyo, Japan will be the site for IPPW 2021 occurring next September. This also is, so bear with us as we try out a new format here, webinar style. We're exploring new ways to collaborate and achieve the objectives of IPPW through virtual communications where possible. So again, we greatly appreciate your participation with us, especially for today's exciting first lecture from Dr. Ralph Lorenz at APL. There will be 6 webinars held, with a webinar held every 2 weeks. 5 of these will be scheduled during kind of normal working hours within the United States, as well as kind of at least reasonable times in Western Europe, Russia, and India. And 1 will be scheduled for convenience, not in the middle of the night, for our colleagues in Japan and Australia. All of these webinars will be recorded, so if you're not able to join us live, no worries there. You'll still be able to access the content at a time that's convenient for you. And lastly, student involvement has always been a key part of the IPPW mission. And our 4th session in the seminar series is specifically targeted for student involvement. So details are still to be finalized for that, but I would direct everyone to the IPPW 2020 website, and you'll see all of the details specific to the webinar series on that site itself. So this webinar series was not something that was originally planned for the content for IPPW 2020 this year. We're a volunteer organization spread predominantly across the US, Europe, and Japan. So I'd like at this time to just continue everyone, to continue to stay safe, stay well, as we work through the challenges of life right now. But I'd like to acknowledge Jim Cutts from JPL. He and his colleagues, which I'll allow him to introduce, have been really instrumental in bringing this web content from something that was an idea just a handful of weeks ago to an actual event that you're all able to participate in now with us over the next couple of months. So Jim and his team's effort, is greatly appreciated, and I think we're all looking forward to the webinar series this year. So, Jim.
Thank you, Ashley. So I would like to acknowledge the efforts of the team. I won't name them all by name because we had a number of people involved. We have one member of that team who's on the webinar today. That's Jacob Israelovitz, who will be handling questions. But we had 5 people from Europe and 5 people from the US working on the program. My main role now is to introduce Athena Costanis of the Paris Observatory, who's going to be introducing our speaker, Dr. Lorenz. Athena has been involved with IPPW from the very outset. She's one of the founding members. She's also a member of our international organizing committee that oversees these activities. And Athena also was a recipient of our highest award, the Alsif Award for 2019. So Athena will be introducing Ralph today. And Ralph, by the way, is one of two recipients of the Alsif Award for 2020. So Athena, please now, I'd like to welcome you to this session and ask you to introduce Ralph.
Yes, thank you, Jim. Thank you, Ashley. Good morning, good afternoon, and good evening, everybody. Very nice to see this high attendance today for this seminar, which is my pleasure to introduce. This seminar is going to be on lessons learned from Huygens, and it will be presented by Dr. Ralph Lorenz. And I'll just give a short introduction from my side. So Ralph and I go back a long way. We met in the early 90s when our paths crossed over the exciting project of the ESA Huygens probe to fly with the Cassini mission that Ralph will talk about today. Ralph had started working with the Huygens project team at ESTEC since October 1990, and then he moved to Kent from October 1991 to October 1994, where he designed and built part of the only instrument of Huygens designed to operate on Titan's surface, and that was the Surface Science Package with John Zernecki as the PI. Jean-Pierre Le Breton, I think he's joined us also today, was the project scientist and mission manager for the Huygens mission. And with him and several of our numerous colleagues in the various international teams, Ralph and I had many opportunities to work together and exchange views over our common interest, Titan. So during the long, almost 8 years Cassini's journey, many of us thought about the satellite, and we sort of placed bets through papers with models and observations prior to the Cassini arrival in 2004. And we followed this arrival and the 13-year mission with interpretations of the precious data and simulations. Titan is an intriguing body, which Ralph and Jacqueline Meaton actually helped unveil, as they described in their 2010 book and the follow-up papers, and has always fascinated the scientists and the public alike. The Huygens probe arrival in 2005 was an amazing experience, and Ralph's and my own paths crossed again at that wonderful event while participating in the Huygens encounter in January 2005 in Darmstadt. So in a sense, Ralph and I have followed the Cassini-Huygens mission for a long time over its duration. And since the beginning of his career, I have been amazed to see how Ralph has been very active in enhancing considerably our knowledge of Titan and other objects in a very prolific production. He has co-authored over 300 refereed journal papers, some in engineering, some in planetary science. And his interdisciplinarity has proven of high importance to our studies of the Saturnian system and more. Ralph has received 7 well-deserved NASA Group Achievement Awards, and as you just heard, also the recently awarded Alsif Memorial IPPW Award. Now, looking to the future, it is really with great pleasure for me and other scientists in our community of Titanophiles that Ralph is also contributing as mission architect to the Dragonfly mission that NASA has now selected as their next New Frontiers mission, and for which Zibby Turtle is the PI. And we really hope to see our favorite place again, up close and personal around the mid-2030s. There is no doubt that experience from the Huygens probe and the whole Cassini mission will help with all future exploration of the Saturnian system and other places in the solar system. So it is really most fitting that the IPPW events that Ashley just described start with such an important informational and scene-setting seminar. Ralph has participated, I think, in every IPPW since their inception, and I'm sure he'll agree with me that the purpose of IPPW in these contrary times is well served by this series of events. So Ralph, I'll hand it to you now. And I just wanted to mention that I also will be responding to questions that are submitting using the Q&A panel after his talk. Ralph, it's all yours.
Well, thank you, Athena, and thank you, Jim and Ashley. Obviously, this is not how we expected to be meeting together, but I think the initiative that Jim's taken has been going to serve us very well. And it's always a pleasure for me to talk about Titan and Huygens. And I see many Huygens colleagues have joined, many ESA colleagues. So greetings across the Atlantic and greetings across the world. So I'd like to take this opportunity to sort of review, what we did on Huygens and what worked, what worked less well, because as Athena noted, there is now a new mission in development where we have the opportunity to apply this experience. So without further ado, let me jump in and figure out how to advance my own slide. There we go. I think there's an intent to make the slides available on the IPPW archive. So I'd urge you to go there because there's a lot of good stuff there already on Huygens. There were some lessons learned and flight experience reports from Miguel Perez-Ayucar and Jean-Pierre and the industry team from the 2005 meeting. All the Huygens data and many useful documents are available on the PDS or PSA. And there are ongoing publications. There's ones I've done. There's some other work, all in the literature. And if people have questions, I'm always happy to answer things by email after the fact. So I'm going to turn the video off now, just to avoid any bandwidth issues and to avoid distracting myself. But anyway, you can look at me partway through this journey. This is actually at Darmstadt in 2005 during the Huygens descent. This is the SM2 model, a special test parachute drop test model that was a useful display prop available at the European Space Operations Center. This is halfway through my Cassini-Huygens journey. As Athena mentioned, I was involved right at the beginning of the ESA project in 1990, and we are now almost exactly one Titan year later, and we're still talking about Huygens. So the orbital period of Saturn around the Sun is kind of what defines these timescales. It takes about a quarter of a year to get from the Earth to Saturn and Titan, and spacecraft developments, including challenging ones like Huygens, are of the order of 7 years. So there's half a Saturn year gone already, and then it took us many years to fully understand the Huygens data. We're still working on it, and of course Cassini operated for, in fact, almost half a Titan year in orbit around Saturn, observing seasonal change. As Athena mentioned, I've had the opportunity to document some of these experiences in a number of books, and there's a Titan book coming out in June with all the sort of best Cassini pictures and syntheses from Cassini. So look out for that. I got involved right at the beginning. I was very fortunate. I remember the notice of my appointment as a young graduate trainee in ESA to work with the Huygens project team. That notice actually came by something called a telegram. Imagine nobody had a cell phone, because almost nobody did back then. And somebody could send you a text message which went to the post office. Somebody at the post office printed it out and brought it to your front door. That was how I was told I got my job in ESA. It was different times. There was email, there wasn't internet, but there wasn't a World Wide Web. There weren't PDFs. All the interfaces between experiments and and equipment on the probe was documented in big, thick books. You know, it was the proposal was a physical truckload of paperwork. You know, the fax machine was used a lot. I remember running down to the fax machine to get updates to the experiment interface document. But it was working on the phase B of the project was a great introduction to the whole enterprise. Even though I went on in graduate school to work on only a very small part of one instrument on Huygens, I could see the big picture. And then I moved to the US in '94 during phase CD, basically, and got involved in Cassini planning. But very importantly, during the cruise, there was Huygens activity prompted by the discovery of a design anomaly, which I'll talk about later. But that reactivation was actually, I think, an important element of knowledge retention, something to bear in mind for future long-duration missions. Just going back to the Saturn year for perspective, you know, we live in trying times right now, but when you start getting old, like me, you can take a long view. I remember the Huygens kickoff meeting in January of 1991 was also the kickoff of Gulf War I. And there was a lot of confusion at the airport because of extra security, and I actually got left behind by the project team. Everyone thought I was in somebody else's rental car. And then, you know, we had 9/11 partway through the cruise to Saturn. So, you know, lots of terrible things happen, but we get through them. And, you know, the enterprise of planetary exploration is one that the whole world looks up to as one of the most positive things that human beings can do. So it's you know, it's a real privilege to be part of that and to share that excitement with you. Cassini had to take the long way to Saturn because it was such a massive, capable spacecraft. So we had 2 Venus flybys, 1 Earth flyby, and the Jupiter flyby on the way to Saturn. The Earth flyby will be important, as I'll discuss. The Venus flybys were important in that they forced the thermal design of Cassini and the Huygens probe to tolerate somewhat high solar fluxes as well as the cold of the outer solar system. And the duration here, as we'll come to discuss, was important in allowing time to develop a solution to an anomaly that was discovered. The mission was originally proposed in the early 80s, and the experience of the discoveries of Voyager at Saturn. Originally, actually, the concept was for a US-supplied Galileo probe and an ESA orbiter, but those roles were reversed. And that meant this was ESA's first entry and descent mission. So there were a lot of technologies and challenges that were new to ESA and European industry. The expectation was of a 2 to 3 hour descent, later shrunk to 2.5. And we had no expectation of what would happen at landing. We didn't know whether Titan's surface was going to be a global ocean of liquid methane, or a huge pile of fluffy dust, or a solid ice surface, or what. There was no basis for designing, at least not for a finite cost, a vehicle that could guarantee operation after landing. So there were no structural requirements for attitude or impact tolerance, but we'll come back to that as well. The requirements, as stated in the Phase A report, were to accommodate a sort of 40-kilogram payload and provide it with power and send its data back. There were requirements on when that descent would begin, the upper atmosphere being of interest from a chemical standpoint. There was a requirement to provide spin to the probe and altitude information. We'll come back to those. The proposal or the requirements called for there to be a telecommunications budget that was positive, power and thermal conditions that would support payload operation for a minimum of 3 minutes after the longest possible descent. So if the thing survived, then there would be the resources to continue operation. But as I said, there was no requirement to stay upright. There was no requirement to tolerate 15G or 30G or whatever. There was sort of a quasi requirement that the probe should float. I don't recall if that was actually a formal requirement or something that just emerged. And obviously, Huygens was a long duration mission, even though it only flourished for 2.5 hours or 3.5 hours. It would need to function, including checkouts, for 10 years. It was intended to be electrically single failure tolerant. Obviously, there had to be exceptions to that. There was a lot of redundancy in the batteries, for example, but you can't have a redundant parachute. So that's kind of standard. The payload in the Phase A study had an ambitious suite that wasn't fully captured. In particular, tunable diode laser spectrometers were too early in development at the time. They're very, very capable instruments now that run on MSL, for example. And some other functions were kind of folded into packages. The atmospheric structure instrument, for example, that was selected kind of embraced lightning and radio emission detection function. That was kind of inherited from Galileo. Analysis kind of showed that probably there wouldn't be lightning, but would you bet your life on it? No, we actually did a lightning test. And then you'll see this surface science package, a very, very small instrument, just in case, right? It would be very sad to land and survive and not be able to diagnose anything about the surface. And in particular, the expected scenario of landing in a liquid left open the question of how much methane and how much ethane is that liquid. And that's something that is still an important question for Titan Cs. But of course, the Cs on Titan turn out to be at the poles, and Huygens landed at the equator. An important point to note, a challenge for ESA compared with developments in the US, is the political requirement to distribute subsystem contracts in the same proportion that ESA receives budget from its member states. So if you're an ESA program manager and you just want the thing to work, then you just get the Germans to build the whole thing and it'll be great. But of course, what you have to do is find 25% for France and 20% for Italy, and then find 2% for Belgium to deliver something for the Finns, their 1%, and so on. So there are communication challenges, there are political challenges that typically aren't confronted in the US. And yet, with the fax machine and the documents, we bring it all together, and we made it work. The challenge is compounded even more for the scientific payload, which is provided for and paid for by the member states, or in the case of the US, NASA. So the organization responsible for implementing the probe, i.e. ESA, has no funding authority over the payloads. And that makes it very difficult to ensure adherence to schedules and standards. I mean, the proposals make a commitment to adhere to technical standards and so on. But there are a lot of difficulties with visibility and authority in ensuring payload development. And some of the payloads were themselves very distributed. The Hazy investigation, for example, was led by Italy, by a PI who then moved to France, in fact, but had contributions from Austria, from Finland, from ESTEC, from the UK, from Spain. So there's a lot of interfaces, a lot of things to track, and that's always a challenge. And yet it was all brought together. The heat shield built from French ballistic missile technology, the thermal protection system was from that arena, mounted on a Spanish-built structure, being held here on an Austrian dolly to go through a door in a test facility in Germany. And the experiment interface document I worked on in ESA was part of managing where all these bolt holes are and where the harness goes and all that. These programs are, of course, full of interesting technical challenges, which is why you were all called in today, because it really is one of the most challenging and rewarding enterprises we can do as a profession. A new thing for ESA was dealing with parachutes. These were sourced by Martin Baker in the UK, and Irvin made the canopies. I think some of the pyrotechnics came from the US. There were 3 parachutes in all, a pilot to ensure transonic stability, and that pulled off the back cover and allowed the main to inflate. The main parachute was sized to let the heat shield fall safely away, but would have led to too long a descent. It would have taken 6 or 8 hours to reach the ground, by which time Cassini would have flown overhead and the relay link would have been lost. So we switched to a smaller parachute for most of descent. It was called a stabilizer, so we'll come back to whether that's an accurate description or not later. This view of the probe in its descent configuration, I don't know if you can, hopefully you can see my mouse pointer. There's a couple of instrument booms from the Haase experiment. These were the only deployed structures from the probe. There are separation fittings that were used to hold the probe to the heat shield and the support structure on Cassini. These are quite bulky, as you see. There are 4 radar altimeter antennas pointing out a transmit and a receive for each of 2 redundant units, 2 relay antennas on the top, and a parachute box. You can also see these little stalks, these little spin vanes. We'll come back to that. Also, let me point out these 3 little stalks, electrostatic discharges, just in case there were charged droplets in the atmosphere. These would let the charge bleed off. You can see these on the trailing edge of Airbus airliner wings. I'm not sure where they are on Boeing's, but they're somewhere. It's a conventional aircraft technology, but again, not something that spacecraft engineers typically have to deal with. On the underside of the probe, there are some gas inlets and exposures of other experiments. And here is DISR, the descent imager that looks out of the side and down. There's a lot of bits to cram into the vehicle. This is actually a generic problem with in situ vehicles like probes, is that they're often more volume constrained than mass constrained because of all the overhead in sitting inside a heat shield and insulation and so on. You want to keep the volume small, and that means very dense packaging. It's a lot of work to figure out how to get all the connectors and the harness in there. You can see 5 batteries here around the periphery. Huygens was designed with robust margins. The design assumed that for power and energy budget that 1 battery would fail, that 1 cell in each battery would fail, and that 1 experiment would fail in such a way that it drew its maximum possible current without tripping the current limiters. So it might be in retrospect that was those margins were over generous. You know, had we chopped off 1 battery, we could have had mass for another instrument. But that sort of thing is very easy to say in hindsight. These batteries had been built, assembled, and launched on Galileo, but they hadn't yet survived in space for 6 years and demonstrated function. So you know, 2020 hindsight is great, but the margins were rather robust here. The camera, as I mentioned, pointed out and downwards, and it therefore had a requirement to spin during descent to pan the field of view around. It also made important measurements looking upwards at the sun to understand how the haze scattered sunlight, how the light was absorbed, which essentially controls the temperature structure, the climate of Titan. The spin is implemented by these little vanes that stuck out of the side, and essentially those force the vehicle to kind of corkscrew around at a fixed number of revolutions per kilometer. You can imagine sort of spiral rails in the atmosphere that just kind of cause a constant rotation rate. So the spin rate in terms of revolutions per minute is therefore notionally proportional to the descent speed, which slows down as you get lower in the atmosphere, and the atmosphere gets denser. You have a discontinuity here at 110 kilometers. That's where we switch from the big parachute and the slow descent to speeding up. And there's inertia involved, so the vehicle kind of spins up slowly and asymptotes back down. So the spin was implemented for the camera, and basically only for the camera. The thermal design, Titan's atmosphere is very cold and dense, and so the vehicle is basically cocooned in a layer of insulating foam about 5 centimeters thick, and we'll come back to that. I don't have too much else to say. There's always an interesting challenge with environmental tests for planetary missions. You can replicate gas compositions to your heart's content, but there are costs involved with that, of course, but you can't replicate gravity. So you have to tune the gas conditions for thermal balance tests to match the heat transfer coefficient, not to match the pressure necessarily. And it turns out that Titan's low gravity more than compensates for its denser atmosphere in terms of heat transfer. So to get the thermal balance right for free convection, you actually want to test a little bit less than atmospheric on Earth. And obviously we're going through these same kind of questions with Dragonfly right now. So I mentioned the insulation. You need to design the vehicle to operate in Titan's very cold conditions. But of course, on Earth, where it's much warmer, that can bring challenges of its own. If you do an operations test, then the vehicle is dissipating power inside the foam, and especially once the radioisotope heater units are attached, you're dissipating a lot of power. So for tests at the launch site at the Cape, there needed to be this duct, this hose blowing cold air through the probe to remove that heat, so the probe didn't overheat during operations tests. Anyway, somebody dialed this air conditioning unit up with 10 times higher airflow than was intended, and the sort of hurricane blowing inside the probe shredded some of the insulation when the vehicle was on the pad, right? This is at the top of the Titan 4 launch vehicle. So Cassini had to be demated from the launch vehicle, brought down, the 100 meters from the top, all kept clean, taken back to the payload hazardous processing facility. Huygens had to be demated, the heat shield taken off, and the inside all cleaned out, which was a very traumatic enterprise to have to do during the run up to the launch. And in fact, the launch got delayed. Instead of launching in the at the beginning of the window in October '97, launch was actually pushed back a couple of weeks. The window was about a month long. So, this was traumatic. It actually had a positive side effect in that launching in the middle of the window meant there was actually more delta V margin for Cassini, which was used to good effect in its extended mission. And in fact, we had to use some of it to fix the radio problem I'll discuss in a moment. Here's the electrical architecture. Huygens had 2 computers, 2 radios, in fact 3 timers during the coast of 3 weeks after it was released from Cassini, when it was flying by itself through space to Titan. Everything was switched off to conserve battery energy, except 3 timers, and so you don't want to sort of miss the event. So there were actually 3 of those, and G switches would have switched the probe on if those had failed. There were 2 radar altimeters, and we'll come back to those. The thinking behind the redundancy was not just against failure, but the thought that if the descent dynamics were vigorous, if there was a lot of swinging under the parachute, then maybe the link would be lost momentarily, that you would have just a break of a second or 2. And there was a lot of attention paid to reacquisition time in the design of the receiver. And the thought was that if one telemetry channel was delayed by 15 seconds with respect to the other, then you could sort of patch across a 10-second gap, and the pendulum period expected was, of the order of 10 to 20 seconds. Of course, that redundant telemetry path was seen as an opportunity by some payloads who chose not to send the same data on both channels. That's a risk, but maybe not an unreasonable bet. We'll see how that played out. So launch was successful, spectacular, pretty, and 7 years of cruise was a long time to wait. And that's an important issue for outer solar system exploration, right? You would like the same team that built the instrument, that built the system to operate it, because they know the ins and outs. But you can't keep a standing army waiting in reserve for 7 years. People move on to other projects. And so keeping the experience base on hand, making sure that the documentation captures everything it needs to, is a definite challenge. Anyway, after the Earth flyby, there was a telecommunications test advocated most particularly by Jean-Pierre Le Breton to do an end-to-end test. There were those who argued that this test was unnecessary, that the radio system had been demonstrated. And what was done was the Goldstone dish was used to transmit a simulated Huygens data stream. And I still remember the Huygens meeting where after this test, where they said, we did the test and no data was received. And we were like, what do you mean no data was received? And it turned out there was a subtlety in the design that really was subtle. It's often quoted as the Doppler effect was not simulated. There's more to that. You can see in this plot at the right that plots frequency shift on the y-axis versus signal to noise. That there are cases where the link would have failed, these red triangles, where if you increase the signal power, it would get better. Okay, that makes sense. But then if you increase the signal power more, it gets worse again. I mean, there are feedback loops, AGCs in the receiver, that mean that this behavior is very non-monotonic. So we were fortunate because we had time, right? There were several years to respond to this crisis. I mean, the crisis basically implied that the mission would not return much data. But there was time to diagnose the fault, to develop a solution and validate the solution. Importantly, there was a full-up engineering model of the radio system, the probe and its instruments at Darmstadt, where designs could be trialed. We could repeat the test with different Doppler shifts and so on in flight. And the issue was actually a quasi-heritage issue, that the receiver on board Cassini, supplied by ESA, was actually inadequate for the job. Early in the Huygens development, there was a sort of variable data rate expected from 0.5 to 8 kilobits a second. In the end, we had 8 kilobits the whole way through, and the receiver wasn't quite up to that, at least not if the signal was Doppler shifted as well. The point being that while there had been tests to show that the receiver would lock happily onto the carrier, the symbol stream was not rate shifted. And the bandwidth of this receiver, which had been used on geostationary satellites where you don't have a lot of Doppler shift, wasn't adequate. And so the cycles would slip and you'd lose lock in the telemetry frames, and the receiver would reject those corrupted packets. And there were parts of that design that in retrospect really should have been designed to be reprogrammable. There was no reason they couldn't have been in hardware terms. So the solution that was developed was to change Cassini's trajectory, which cost a lot of fuel, cost 86 meters per second, and entailed a lot of redesign of scientific observations of Cassini. But by changing the orbiter trajectory and thereby changing the miss distance from Saturn, you basically introduce a cosine term in the Doppler shift that reduces it. There was another mitigation, which was to switch the probe on early so that it warmed up the quartz oscillator that drives the symbol rate in the receiver, in the transmitter. Has, like all quartz clocks, a frequency dependence, and so by switching on earlier, getting a little bit warmer, you push the frequency in the right direction. And the result was that the expectation for the mission would have the frequency and amplitude line between these shark's teeth. So you can see how that worked out. There's a great documentary about Huygens called Destination Titan that you can see on YouTube. And if you go to about 50 minutes in, the sort of crescendo of excitement, there's this scene of the operations center with a lot of politicians and high mucky mucks applauding. And you can see in the foreground, Claudio Salazzo, the mission operations manager, sort of looking, puzzling at a screen in front of him. And everyone's clapping because they've seen data start to appear on the screens. But actually, only one of the two data streams seems to have worked. And Claudio kind of is looking worried at his screen and then sort of starts clapping under the influence of peer pressure. It's a sort of interesting social dynamic. Anyway, what turned out was that while we'd corrected that Doppler issue fine, it turned out that of the two telemetry channels, one was lost altogether. And that was because it had a dual function, which was sending the telemetry, but also measuring the Doppler shift very accurately to infer the winds on Titan. And that was done by having a payload provided, a member state provided ultra-stable oscillator on the transmitter and a corresponding oscillator, rubidium oscillator, on the receiver on Huygens. And so by slaving the transmitter and receiver to these oscillators, you can compare the two and get a very precise measurement of the Doppler shift. Because the way ESA works, and these are member state provided payloads, it was assumed that there was no guarantee that they would show up on the launch pad at the appointed date, or that they might fail. Right? Payloads are sort of held to a different standard to equipment. So there were switches. Right? There were switches that said, well, if the TUSO isn't here, then we'll use our onboard standard oven-controlled oscillator like channel B. And so there's a switch on each of these, and the switch was correctly placed to slave the receiver to the RUSO and to slave the transmitter to the TUSO, but the command to power the RUSO on was somehow omitted. And this was a one-off command sequence for the probe relay, and somehow this was not caught in testing or validation. And that's something to carry forward for future missions. Really have a way of doing a full rehearsal. So that was a frightening loss, but because of the redundancy, fortunately, most of the instrument telemetry was recovered. The Doppler measurement could not be done on board, but because some large radio telescopes were used to sort of listen in on the Huygens signal, the principal objectives of the Doppler experiment were recovered. There are bigger gaps. There is poorer time resolution in the Doppler profile than we should have got. The camera sent images on both channels. It was logical to send different images on the two channels, so there was essentially a 50% decimation of those. There's a subtle atmospheric electricity measurement that I don't have time to get into that was perhaps not optimally configured to exploit the two channels, so some high sensitivity data were lost. But several of the payloads were essentially unaffected. But all in all, the mission was a great success, and the data set largely met what was intended. Okay, I better speed up. So the spin, as I mentioned, this was designed to pan the camera around. And as we started to put the different images together, I remember the imaging team asking the question, is it possible the probe spun the wrong way? And it took work by Miguel Perez-Ayutar to confirm this from the radio link AGC data, that in fact, not only did the probe deviate from the line here, the smooth line, the expected spin profile, but it actually spun down faster and then spun up the wrong way. The impact overall scientifically was not large. It was really a burden on scientific analysis, which you can equate to phasey dollars, if you like, as somebody else's problem. But it's a distressing anomaly. And it's actually only been fully diagnosed in recent wind tunnel tests that ESA supported at Orléans, in fact, where Jean-Pierre is. And these show that an assumption that had been adopted in the development that these flat, horizontally flat radar altimeter antennae wouldn't have an effect on the spin dynamics. That was wrong. What turns out is that they sort of focus the airflow over these asymmetric attached fittings, and torques caused by that airflow interaction, which was only really disclosed by 1/3 scale models where you could take these fixtures on and off and do them in different combinations, showed that reverse torque could overcome the spin vanes. There's another effect, which is that it seems that at least one of these booms was not deployed correctly for at least part of the descent. And as you can see, this relaxation probe, this flat disk, could act as a pretty strong wing to affect the spin dynamics. And there's some simulations that I actually did in 2006 to try and make sense of what happened that we've armed with the wind tunnel data we can now explore in more detail, that require several changes of aerodynamic configuration during the descent. Probably at least one of these is related to the boom not deploying and then deploying, but there's more things going on too. I think there's something about the interaction of the probe weight with the stabilizer parachute. And there was a test of all this. There was a balloon drop test in Kiruna in 1995. It was on the critical path for launch. So the project really wanted to show that the pyrotechnics and the chute inflation and so on would all work, and they did show that. And there was perhaps less attention paid to the details of the dynamics, but indeed when we got to Titan, we saw, at least for part of descent, that the motions were really rather vigorous. Remember, when Huygens was designed, there had only been Viking and Pioneer Venus as Western planetary parachute descents. There really wasn't a lot of available data from the Russian missions. There wasn't the big experience we have with the Mars missions now, with IMUs and 18 degree of freedom models and Monte Carlos and all that. So the high frequency wrist mode or scissors mode motions were not understood. And had they been understood, we might have designed the sampling strategy, the software, to document them rather better. But they were evident in this parachute drop test. You can see on the left the dynamics, the rates under the main parachute were relatively benign. But as soon as we dropped onto the faster descent, there's a lot going on. And had we fully appreciated that, we might have changed our data acquisitions strategy a little. And Steve Lingard, now at Vorticity, I think made some important simulations with tools that were not available, a decade before, that show the wake interaction with the parachute during some parts of descent, seem to reproduce this motion. So we at least understand some of that destabilizing effect of the stabilizer chute pretty well. But it's important to remember in the lower atmosphere towards the surface, the descent dynamics were really quite benign. I better reach a close soon. The radar altimeters turned out to have a behavior that was really only disclosed in a balloon test just weeks before the actual Huygens descent. They had a situation where they could lock up, essentially indicating a false altitude. Fortunately, that didn't trigger any payload operations out of the plan, but there was definitely a lesson learned about test as you fly. One of the payloads, the aerosol collector, I think had what must be considered disappointing results. It was sort of a vacuum cleaner that sucked in air and trapped aerosol particles, then pulled that material into an oven and baked it to sweat out the organics for analysis by another instrument. And that sort of sample handling, sample acquisition and sealing is always challenging. And it seems that basically the sample was lost, that a seal failed. A silicone gasket probably didn't seat correctly because it was too cold, and things worked later, but by then the sample had been blown out by the flushing gas. So, you know, this is something that's much harder to do on a probe than a lander or rover, because, you know, the probe only has one chance to make this work in real time. On a landed mission, you have an opportunity to, you know, develop workarounds and so on. But that was a difficult instrument to implement, and it did have difficulties. I'll skip that. Yeah, in-flight checkouts were very worthwhile. We did them once every 6 months on Huygens, and the trending of instrument behaviors was important in their calibration. There's a sun sensor that lost sensitivity because of radiation effects. We don't know whether it's these in-flight checkouts had lower output because the stimulus degraded in efficiency or the detector degraded, but we could at least see in advance that there were some effects of cruise radiation. And these checkouts had the advantage of, you know, waking the teams up and keeping them engaged, so you knew which drawer of the filing cabinet all the Huygens stuff was. So when we got there in 2005, we knew where to find it. There were some subtle interactions of the way the camera's compression scheme interacted with the fiber optic bundle that mapped the light onto the detector. That's kind of a subtlety associated with that particular implementation, but the subsequent processing of the images, I think, led to very good products. But one thing we got wrong was not planning for the best. Because there was no guarantee of survival of impact, the camera strategy was to empty the buffer, to land without any data stored internally, because there was no guarantee that you'd get that data off the probe. But that meant that we didn't take any data in the last, any images in the last few hundred meters of descent. And that data would have been really interesting to see. What we got instead, of course, was hundreds and hundreds of copies of the same post-landing scene. So it was a conservative approach that maybe shouldn't be questioned too strongly, but it meant we didn't exploit the full potential of what the descent offered. Of those 100 images, there was actually a little bit of science output in that there was one change in one image that may have been a methane dewdrop that formed on the camera baffle. Lastly, there was another little science output from the radio behavior. You can see the spin modulation of the signal strength during descent as we moved out of the shark's teeth. And then after landing, that spin stops. But the radio signal strength didn't vary monotonically. There was a sort of bump of up and downs. And that was not anticipated. Probably should have been, but it wasn't. And Miguel and I and others actually could analyze that. There was a multipath effect that let us diagnose how high the probe was sitting above the ground and some of the radio reflection properties of the ground. So you know, there's a lot of things that can happen that are positive as well as negative. So I better wrap up. Huygens was a great success. There were a lot of things that didn't work as planned, but were not fatal. It's important to look closely at your tests. They're an opportunity to figure out unknown unknowns, not just check a box. And you know, the analysis of Huygens data are still going on, and they have needed things like wind tunnel testing. You know, the mission isn't over when the downlink stops, so prepare your post-mission budgets for that. So thanks for your attention. I hope this was useful. As I say, I'm happy to follow up by email afterwards, as well as by the Q&A platform on this WebEx. Thanks for joining.
All right, thank you, Ralph. For those of you who have any questions, feel free to type them into the Q&A.
Can't believe there are no questions. Oh yeah, while we're waiting, I can go back to a couple of slides I skipped over. Yeah, here's one. The Surface Science package had an acoustic sounder, an echo sounder, that was really designed to measure the depth of the sea if we landed in a sea. But it did operate in the atmosphere and picked up an echo from the ground, actually from 100 meters up, 90 meters up. We had hoped to use it to pick up echoes from any cloud layers during the atmospheric descent, but during part of the descent, a lot of the sound was kind of blanked out by noise from a pump on the ACP. I don't know how we didn't anticipate that, how that wasn't picked up in tests, but somehow it wasn't. Okay, looks like there's some questions. Do you want to pick one, Jacob?
Sure, let's just start with Andrew Balls. So can you tell us some about SSP?
Can I tell you something about it? Well, Andrew knows SSP very well, of course. But with respect to lessons, because SSP was an interesting challenge because it was originally designed with the expectation of landing in a liquid. And I think the different measurements that it made on dielectric constant or refractive index were all biased towards liquid, except perhaps the penetrometer. And had we been more open-minded, perhaps, originally we might have developed a broader set of measurements that would have been more interesting for a land landing. But again, that's easy in hindsight.
All right, so we have another one that's been asked a few times. Can you maybe give some examples of how lessons from Huygens are being carried on to Dragonfly?
Yeah, I think the bullets here capture that. I mean, knowledge retention on a long mission. Dragonfly will launch in 2026. Will arrive in 2034. That's a long time to maintain the tools. So we are definitely, I've been vigorous in saying, we should have checkouts frequently just to keep the teams active, and we need to plan for that. Another point is the tests. There's a great temptation to see tests as a box to be checked, right? A program manager just wants to get the test done, validate requirement X, move on. But they are a way of finding out what you haven't thought of. So it's better to do more tests without making them 99.999% high fidelity. It's better to do 10 tests that are 95% fidelity and really understand what's going on. Probably those are the two big lessons.
And on that front, this is a question from John Zarnecki. Given that there was a full, so given that there was a full dress rehearsal, is the telecom issue, was that one of those 5% issues that wasn't picked up?
Yeah, so I recall David Southwood, the director of science at ESA, saying there would be an inquiry into the commanding error, and I'm sure there was, but the full examination of the steps in the command generation and validation, I think there's not been a public report on how that happened and what opportunities were missed. the only defense against it is full hardware in the loop rehearsal, but that's hard to do if the probe is still attached. But it's definitely a lesson that was being carried forward to other proposed probe missions.
All right, I'm going to jump ahead to Michelle Monk's question here. Is there anything specific you're doing to engage or pass on knowledge to younger scientists and engineers in the Dragonfly project?
Right. Well, hi, Michelle. Congratulations again on your ALSEIF award. Part of our proposal to NASA for Dragonfly included a science enhancement option, which was some program options to engage other scientists not associated with the original proposal in mission development and flight operations, not just scientists but engineers as well. It's up to NASA headquarters quite how many of those to fund and and when. But yes, we do have an intent to engage the wider community and bring in flesh and blood.
All right. A question from Athul. Could you explain a little more as to the reason that the buffer had to be empty on landing and why that led to the no images taken just before landing?
So the most important thing scientifically in the last part of descent was felt to be not imaging, but spectroscopy to get a measure of the composition of Titan's surface that wasn't affected by the thick atmosphere. So I think most attention was focused on that. But the reasoning was that any data that is in the buffer at landing might be lost. So we don't want to lose anything, so let's not have anything on the probe at impact. But there wasn't the sort of thinking through of, oh, well, if we do survive, then, how does that data compare with the images we'll take subsequently? So there was a little bit of a failure of imagination, I think.
All right. Maybe one more question before we close out here. This is from Gregory Pinaud. What is the REX on the front heat shield TPS thermal protection system?
I'm afraid I don't quite know what REX means. Is it this picture? Oh no, that's at the back. I'm afraid I don't quite know what the question is pointing at.
I think I might be able. Let's see. If Tim Brights is still online, he might be able to unmute Gregory to ask the question directly.
Well, this is an experiment in real time.
This is an experiment in real time.
I see another question, meanwhile. What is the science or engineering outcome from Huygens that's still being studied? Actually, the atmospheric electricity measurements, the Schumann resonance, that was measured by these booms, actually, is something that we're exploring. I think it may be that actually a lot of the signal there was generated by the probe descent. But there are some important things about atmospheric electricity that we're carrying forward to Dragonfly. We're going to attempt to make the same sort of Schumann measurement over longer duration. Did we get the questioner online?
I don't think so.
Okay.
This is why we've been having this is why we've been having me just read them just to double check. Here's another one from Andrew Ball. Is the radar altimeter data now fully understood, or is there still something unknown there?
I think the mechanism was understood. There was a digital issue that basically caused the things to read double once they locked up. There were two altimeters. and there was a prediction, the DDB, of where the probe was expected to be. Then once the altimeters locked up, the sort of majority voting caused the estimate of altitude to be where the two altimeters were saying it was, which were both wrong. Then altimeter B recovered and read the right answer. So these raw outputs were telemetered, but the red line is the real-time estimate. But the real-time estimate then was kind of voted out by where it thought it was and where the other altimeter was saying, and only recovered when the other altimeter recovered. There's little history here, which is that the altimeters were only specified to work down here, and had they been turned on approaching there, they would have probably locked up correctly. But scientists, being the curious individuals they are, they said, well, let's turn them on early and see what we get, without appreciating that there was this undisclosed behavior of the two that was only demonstrated in a free space test on a balloon. I don't know if the internal mechanism of the failure is fully understood. I think so, but I don't recall the details. But it was a subtle business.
So we have a clarification from Jean-Marc that Rex's return experience lessons learned. So
yeah, there is. There is. Well, here's the heat shield. I think the main lesson about the Huygens heat shield development is that it was done in a period, an environment where very little was known. There were uncertainties in the atmospheric composition. In particular, the amount of methane in the atmosphere drives the radiative heat fluxes. And the tools to estimate those heat fluxes were relatively immature. So the heat shield had to be designed with large margins, prudently. But we actually have no real measurement to confirm how big those margins were. Did we almost burn through the heat shield, or did we carry 50 kilograms of extra TPS that we could have replaced with instruments? And that's something that ESA did not have a requirement for what's now called the engineering science investigation, which competed NASA missions do, and Dragonfly has, which oblige missions with entry systems to document their performance. So you put thermocouples in the heat shield material. You have an IMU to characterize the body rates at parachute deployment, which fold into how Schiaparelli had a bad landing. You can't fault Hamid Hassan, the ESA project manager, for not putting instrumentation in the heat shield. There was no requirement for him to do so, but I think it is a good requirement to have. And of course, one of the few returns from the Schiaparelli mission is some of the entry system instrumentation, the DLR package. So probably that's the main lesson.
Okay, maybe one more question just to close out. Bring back to Dragonfly, because I think that's obviously on all of our minds now. Special points of interest in Titan exploration from the Dragonfly mission.
Well,
maybe answer some unanswered questions from Huygens.
Well, absolutely. So the thing that we have known even from the mid-90s that Cassini-Huygens would not do very well, was not equipped to do very well, was tell us what that surface is made of. Yeah, there's some bright stuff and there's some dark stuff. The spectra taken by Huygens during descent constrain the composition a bit, but the interpretation is not unique. And we can see right here that it's a diverse surface. There's highlands, there's lake bed, stream bed that's dissected. So the big thing Dragonfly is designed to do is to hop around and sample this dirt and see what it's made of, what interesting organic, possibly prebiotic chemicals are in there. So that's the big question, and it's the question that we knew we would have after Huygens. Huygens had a heated inlet on the GCMS instrument, the gas chromatograph mass spectrometer, that did sweat some volatiles out of the ground. which gave us some interesting hints. So there's methane and ethane moisture there. But is that particular to this stream bed that we landed in, or is everywhere like that?
Well, I would like to thank Ralph for this superb presentation today. To thank Athena for her words of introduction. And I'd like to tell you a little bit more about the next session we have planned in 2 weeks' time. This session, you'll be interested, will include aerial exploration to 3 bodies. Titan with Dragonfly, Mars with the Mars helicopter, Venus with a proposed Venus balloon, which is still being studied. So we'll have presentations on all 3. We don't yet have the registration information up on the website. We hope to have that up in 2 or 3 days. So we encourage you to come back to the IPPW 2020 website in 2 or 3 days and register. So thank you all for attending today. Thank you for your questions. And we look forward to further successful sessions of the IPPW webinar series. Thank you.
Thanks for the nice talk. Thank you.
Thank you, Ralph. Bye.
Thanks, everyone.
Thanks.